Previously, we introduced the notion of catenary rings, and we looked at an example of a ring which is not catenary. Recall that this ring was the coordinate ring of the union of the z-axis together with the xy plane in A3. It's not catenary because it has two maximal chain of prime ideal of different lengths. For example, this chain here corresponding to the inclusion of the black point inside the z-axis is of length 1, whereas this chain here, which corresponds to the inclusion of this blue point inside the x-axis, which is then included inside the xy plane, that chain is of length 2. Since not all maximal chains have the same length, the ring is not catenary. And intuitively, we see that the issue here is that this algebraic set is not irreducible. Algebraically, this means that its coordinate ring is not an integral domain. Actually, we can see by Chinese remainder theorem that this coordinate ring breaks down into a product of two rings. One part could be viewed as the coordinate ring of the z-axis, and the other part could be viewed as the coordinate ring of the xy plane. Maximal chain of prime ideals on each of these parts have different lengths, and that's where the issue comes from. So we'd expect that we will not have this issue with irreducible affine varieties, and that's indeed true. It turns out that the coordinate ring of any such variety is gonna be catenary. To prove this, we just need to prove the following two propositions. The reason is because every finitely generated K-algebra is going to be a quotient of some polynomial ring by some ideal, and that finitely generated K-algebra is an integral domain even only if the ideal that we are quotienting by is a prime ideal. So if we can show that any polynomial ring is catenary, and the quotient of any catenary ring by a prime ideal is also catenary, then any finitely generated K-algebra that is an integral domain must also be catenary. Now this proposition here is obvious from the definition of catenary because any two maximal chain of prime ideals inside this quotient would correspond to a maximal chain of prime ideal from P to R. So let's say we have two such chains. Then we can combine them both with some maximal chain of prime ideal contained inside P. Now each of these combined chain is a maximal chain of prime ideal in R, and R is catenary, so these two combined chain must have the same length, and hence these chains must have the same length. Thus R over P is catenary, and that argument also shows that the height of P plus dimension of R over P must be equal to the dimension of R. So now it remains to show that the polynomial ring is catenary. And we'll do that in the next video.